in problems like turbulence, and in fact in many areas, there's more and more data being collected. There's bigger machines to store things, there's accessibility to lots of information. What do you think one can glean from this information in terms of trying to understand some basic mathematical issues?
Well, as far as turbulence is concerned, the answer is probably very little. I think there's a practical question. There are lots of practical questions. You have lots and lots of data. You may want to draw from them practical conclusions about designing aircraft or boats or stuff without necessarily, well, there are lots of techniques nowadays which basically allow you to take experimental data and interpolate by them for practical situations. And that's a useful enterprise. That's a useful endeavor. Not one which I'd be particularly eager to work in, but it's useful. But the general issue is the one of understanding. For example, suppose you could do a brute force calculation. Forget about data from the experimental world. Suppose you could buy a large enough computer. It's not anywhere in the future, and do a sufficiently refined calculation. So in fact, the output looks like turbulence. What have you learned? And the answer is nothing. Because it's no better than trying to make a wind tunnel and look at the turbulence. You look at the turbulence and there's not much insight in there. There are exceptions to that. There have been a collection of experiments, in particular at Stanford, distinguishing what kind of structures exist in turbulence. It's trying to simply photograph it well enough to suggest possible structures and possible ways of representing turbulence which are more efficient than other representations and which give you some insight. It's all in the realm of the possible. The big discovery from experiment. Okay, so the experimentalists think that they have discovered organized structure in turbulence, which in fact, if I may say so, I saw several years before that in the vortex calculations, to some extent. But of all the large vasts of amount of experimental data about turbulence which have been accumulated, there are very few which give you some insight. And the issue is insight. There's also this big trend in science that you really can make predictions without understanding anything. As you mentioned some things. Neural networks, weather forecasts, for example, which make no attempt to figure out what the mechanics of the atmosphere are, or what the forces at play are, and what's important. You simply collect lots and lots of data, and then you write a program which classifies the data, and when in a given situation finds the set of data which is closest to what they're seeing, and makes a prediction on that basis. And that gives rise to philosophical questions. What's understanding? I had lectures I used to give about the limits of understanding. In classical Newtonian mechanics, you have a feeling you understand. Bodies which attract each other at a distance make sense. You can imagine some imaginary rope connecting the sun and the moon and Earth, and you have some understanding. Things attract each other. So it has a heuristic value. Quantum mechanics, it's a set of rules, abstract rules. What do you mean? No one understands quantum mechanics. You get used to it. You learn how you used to calculate. You understand. But it's not the same understanding as an understanding of classical mechanics. You have an abstract theory in which you say, and what do you mean? What does it mean to understand? So you may actually, somewhere along the line, get the ability of reproducing turbulent flow by computer program and matching data, and that will be an achievement. And this will be understanding. It's not so clear. And actually, I'm doubtful that you can actually achieve that kind of imitation of nature without actual insight.
Well, I think there's that, and there's also that the point to a mathematical model is not simply to be able to predict data, predict solutions that's within the range or bracketed by the data you have, but actually to go extrapolated far further outside a place where there isn't information. And I think there, the notion of pattern matching immediately is seen to fail.
Yes, absolutely, I agree with you.
There is a difference between an answer and understanding as to why that answer is correct.
Yes, I agree with you entirely. Certainly, I 100% agree. Except the understanding is becoming generalized, and where does the boundary lie between the notion that between you being able to say that you understood, your ability to write a computer program that produces something which looks like what the thing you're trying to understand? That's not clear to me.
Well, there's the Yogi Berra quote, and I can't get the order right, which is you can observe a lot by seeing, or you can see a lot by observing. But whatever. I mean, there's a reason to look at the real world and see what comes out of it. That's one type of understanding.
Well, the work with Grisha, certainly that model of turbulent shear flow came out of the looking at data. I mean, people made measurements and Reynolds numbers higher than before, and this was something unexpected. And the question was, how do you explain that? And so we came up with some explanation. The explanation is not, it's a scaling explanation, so it's not really a mechanical explanation. It's not a full explanation, but it's a mathematical model. So data help occasionally. But it's tricky. I mean, it's not clear-cut. On the whole, I think that data don't give you explanations. But maybe they raise questions, but not explanations. But it's not absolutely clear-cut.
No. It also is a surprise to people to discover that data isn't always true.
Yes.
There's errors, there's misunderstandings, there's inaccurate experiments, there's poor measurements, there's all sorts of things. So,
well, in fact, this work I've been doing of late about the data simulation is a way to try to clean data, get data which are unreliable, and models which are unreliable, and try to conclude from them something which may not be completely false.
There's a bit of a philosophical worry in that. So if the data isn't necessarily right,
yes,
how do you find a model that will be more right than the data?
No, that's not the issue. The issue is, suppose you have a model you don't trust and data you don't trust.
So there's degrees of trust in what you're saying here.
Yes. And suppose, out of the two, can you get something which you trust a bit more than you trust either one? That's really the question. So it answers, well, you have to do it right. I go around giving a talk which is called Why Predictions Fail, which I try to discuss how people make predictions for economic predictions, climate predictions, stuff. So they have models which are noisy, and they have data which are noisy. And so to make a prediction, you need both the model and data. And of course, the problems of the two. So the models may not be good enough, and data may not be good enough. On the other hand, the issue of how you put models with data correctly has not been properly addressed. Just about all the software that's being used to make any kind of prediction depends on some mathematical assumption, which is, I'm not sure what, separation of scale, which justifies what's being done, which is invalid. I mean, it's valid under particular circumstances, but it's valid much less than the range of things which are where it's being used. In particular, in economics and finance, they make assumptions of separation of scale which are totally legitimate. And the reason why they do that is, of course, doing it correctly has not been fully explored, and from everything we know, it's very difficult. Time-consuming, mathematics-consuming, computer time-consuming. So there's even trying to draw conclusions from data is at this point a mathematical question which has not been properly addressed and has not been solved. And so that's something which requires work. And I'm hoping to make a contribution, but of course not nearly sufficient.